Recording, go ahead.
Okay. So, good afternoon, everybody. Thank you for joining today's NC-CAV seminar on application of AI to CAV operations. Today, we are delighted to have Professor Samuel Labi and Dr. Sikai Chen as the speakers for today's seminar. A little bit about Dr. Samuel Labi's background. He's a professor at Purdue University School of Civil Engineering and associate director of the US DOT Region 5 Center for Connected and Autonomous Transportations. Dr. Labi's research is guided by current and evolving trends on civil infrastructure development landscape. His research include DOT, US DOT, TRB, Rhode Island's State Attorney General, and Illinois' Auditor General. He serves as assistant editor, editorial board member, or guest editor for journals including Computer-Aided Civil Infrastructure Engineering, Safety Science, Infrastructure Systems, Risk and Uncertainty. He's the chair of ASCE Economics and Finance Committee, secretary of TRB's Asset Management Committee. Dr. Labi's major research awards include American Society of Test and Materials ASTM Mother Award of 2007 for outstanding paper in concrete materials, TRB's KB Woods 2008 for outstanding journal paper in design construction, ASC Frank Masters Award in 2014 for outstanding and innovative work in advancing the areas of transportation systems, and so on. And also, we do have today Dr. Sikai Chen, who is a visiting assistant professor at the Center School of Civil Engineering at Purdue University and visiting research fellow at the Robotics Institute School of Computing Science at Carnegie Mellon University. He received his PhD in civil engineering with a focus on computation science and engineering from Purdue University in August 2019 under the supervision of Dr. Labi. Dr. Chen's research interests span both theoretical and applied aspects of artificial intelligence, data science, robotics, optimization. His research application areas include connected and autonomous vehicles, transportation and infrastructure systems, human factors, smart cities, cloud, fog, and edge computing, autonomous vehicles, transportation and infrastructure systems, and cloud and fog edge computing for larger scale network modeling and simulation. His PhD dissertation was on safety implication of roadway design and management. So with that, I did not go through the whole bio. I think as already is very impressive to have both Dr. Labi and Dr. Chen as a speaker. I would like to thank the sponsors of the project, Downtown Greensboro, Verizon, and RTI, and importantly, North Carolina Department of Transportation for supporting this project. With that, I'll pass it to Dr. Labi.
Okay, thank you very much. We are very honored to be invited to this August series of seminars, and for your introduction. And I also thank to all members of the audience who are here on a Friday afternoon to hear us speak and also to engage in a conversation about autonomous and connected vehicles. Now I'm going to put off my video so I can maximize the quality of my audio. So if that's okay, I'll do that. So I'll stop my video and then we can shoot off right away. So let's do that. Stop video. Okay. All right. So if you can go to the, okay, so this is a cover, prospective application of artificial intelligence in CAV operations. So Sikai, if you can go on to the next page, please. Next slide. So first of all, I would like to introduce to you the USDOT Region 5 Center for Connected and Automated Transportation, CCAT. This is a regional UTC that was established in 2016 based on an award from the USDOT's Research and Innovative Technology Administration called RITA. CCAT was established to advance research in vehicle automation and connectivity, and therefore we seek to address transportation problems that are related to safety, mobility, and sustainability. The director of CCAT is Dr. Henry Liu of the University of Michigan. Now, there are three parts to our mission at CCAT. The first is education and training of the future workforce related to automation and connectivity. The second is the transfer of technology. And the third is research, on which I will elaborate after the next slide. So if you come to the next slide shows our partner institutions of the center, the consortium. So we have the University of Michigan, we have Purdue University in Indiana, we have UIUC, Champaign in Illinois, we have University of Akron in Ohio, we have the Central State University in Ohio, and Washington College in Michigan. So if you can go to the next slide, you see there are 6 groups of activities that we carry out. Research activities, of course, research activities that we carry out at CCAT. The first is enabling technologies, where we look at, for example, machine learning, AI, and any other technologies that would support connected and automated transportation. We also do the second cycle there, policy and planning, where we do demand assessments and market surveys, supporting regulations from government, ethics, and so on. The third is the human factors, where we examine issues related to human-machine interface. For example, warrants and mechanisms for human takeover from automation and vice versa. The fourth bubble there is infrastructure design and management, where we examine some of the physical and cyber facilities that are needed to support automation and connectivity, and some changes in design and maintenance standards and lane management and so on. That would make the infrastructure more prepared towards CAVs. The fifth bubble there is operations and controls, where we design AI-based controllers to facilitate safe and efficient movements of the CAVs. And the last is modeling and implementation, where which basically addresses the deployment strategies that are very important in order to support the attractiveness of CAVs. So those are the 6 areas of research activities that we carry out at CCAT. Now, if you go to the next slide, please. So the fundamental motivation for vehicle automation and connectivity is the persistence of long-standing transportation problems. For several decades, we have been faced with 2 primary problems in transportation: traffic delay and safety. Traffic delay leads to loss of billions of dollars through energy waste, fuel waste, through loss of tracking productivity, through emissions. If you can quantify it in dollars, yes, it costs a lot of money, billions. And with safety, the safety numbers are still high in the US. We are still running over 40,000 as of last year. Last 2 years, it was 42,000 fatalities. That's still way too many. And 2 million injuries, traffic injuries in the US. Globally, it's even much more bleak. We have 1.2 million fatalities every year globally, all over the world. And 95% of all crashes have been found to be related to human error. Of course, there are those factors like the environment, the roadway, the vehicle, enforcement, and all that. But when a crash happens, it's often the interaction of several factors. And human error has been found to be either the main cause or a supporting cause of some of these crashes, a majority of these crashes. So it's an issue that is still persistent and needs to be addressed. And the hope is that automation and connectivity can help to resolve, to mitigate, if not eliminate, some of these problems. All right, so if you go to the next slide. Okay, so here I'm preaching to the choir because many of you already know what is vehicle connectivity and automation, but this is just a quick review, all right, for most of us. So with vehicle connectivity, vehicles are able to talk to each other, okay, to talk to other vehicles so that they are aware of the presence, proximity, speed, direction, and other attributes of other vehicles within some specified radius. Not only do they talk with other vehicles, but also talk with the infrastructure and pedestrians. You know, with pedestrians, they talk to them through their smartphones and other devices. Vehicle connectivity also makes it possible for drivers to receive notifications and alerts of any threats and opportunities in the traffic environment, downstream or at other locations in the network. And the next slide talks about automation, vehicle automation. I think it's a video. So if you can play that video, Sikai, please play the video. So on the video shows a vehicle, an automated vehicle moving on an urban arterial, and it is sensing all the threats and opportunities. The boxes you see, the yellow box there is a cyclist. So it has perceived it, and it's moving in a way that avoids any conflict with this threat. So that's one important aspect of autonomous vehicles. Just like human drivers, as we drive, we are looking out for threats, but also opportunities that can reduce crashes or enhance our mobility. Okay, so with vehicle automation, particularly, if you can please stay on slide 7, please. Let me just a few things there. With vehicle automation, particularly levels 4 and 5, like I said, the vehicle, like we know, the vehicle is intended to operate without direct human involvement, and the driving is carried out using AI-based control systems. Okay, now we can go on to the next slide, please. So the next slide is about the sibling relationship between automation and connectivity, and their holistic nature is represented in cooperative driving automation, or CDA. Some research in the literature have shown that using computer simulation or test track experiments, cooperative driving automation can have some benefits. It can help improve transport efficiency and mobility. It can help facilitate track movements, help increase safety and productivity, and possibly even reduce the need for some kinds of roadway infrastructure. So when I say holism here on my slide, so the holism here means that automation and connectivity can give us a synergistic benefit. In other words, the effect of the sum can be superior to the sum of the effects. Okay, the benefits of CDA is superior to or is more than the benefits of automation only, plus the benefits of connectivity only. So we haven't proven that is a supposition, but from current research literature, that's where it's driving at, and we are expecting to be in a position where we can prove this synergy or holism, either us or other researchers, and that would be a very big accomplishment for whoever does it. Okay, so if you can go on to the next slide, please. So this slide here is just a recap of the previous slide, a repetition of the previous slide. So I'll not belabor the point here about the holism. So if you can go on to the next slide. Okay, so from the perspective of intelligent control for automotive driving, there are generally two types of AI systems. The first one is imitation learning. The second is reinforcement learning. So let's talk about both. For imitation learning, we need to collect data on how human drivers drive, basically, right? What decisions they make under which traffic situations, in terms of, for example, turning the steering wheel, pressing the gas pedal, pressing the brake, etc. So after we collect this data on how humans drive, we use the data to train an AI system, and the AI system learns from that data so that the AI system imitates the human drivers based on the collected data. Now, the good thing about imitation learning is that it's generally easier to design the AI system and also much easier for the algorithm to converge. On the other hand, imitation learning does exactly what it's supposed to do. It imitates human driver behavior. And therefore, it's only as good as the driving behaviors of the human drivers that generated the data. The developed AI may not be able to do better than those human drivers. So if the AI is learning from a bad driver, then it's going to have a bad performance. It's as simple as that, you know. So that is the downside, you know. The second way, just like I said, of intelligent control using AI is through reinforcement learning. And this has become increasingly promising recently due to an increase in computing power. So here, what happens? What happens here is that the AI learns by itself through trial and error by interacting with the environment. And in fact, researchers across different domains have shown that reinforcement learning has great potential to outperform human experts in doing various aspects of the tasks, including driving. One disadvantage, though, is that reinforcement learning algorithms are generally difficult to design to make it learn very well, you know, much more difficult than imitation learning. And it's more difficult for them to converge. Okay, so those are the two types of classifying AI in the context of AV learning. Now, on the next slide, this is a list of 3 contexts in which we, as in the researchers at CCAT, Sikai's group, have applied AI in the context of AV operations. The first one is CAV control, where we have developed innovative AIs for multi-agent systems. The second one is where we have used CAVs, or we have shown how to use CAVs to mitigate congestion in a mixed stream, you know. And the third one is a framework to help the CAVs avoid collisions under situations where a crash is imminent. So those are the 3 contexts. I'm going to hand over to Sikai now. You're going to present some detail on each of these. And after that, we shall take your questions, your suggestions, and any comments. Okay, Sikai, over to you.
Yes, thank you very much, Dr. Labi. Now I'm going to start with the first example, which is the developing innovative AI for the multi-agent systems. So in a traffic system or a traffic network, you'll know that we will normally have like multiple vehicles, and some of them will be the human-driven vehicles like what we have right now, as indicated by this white color. And in the future, we will also have the autonomous vehicles in the mixed traffic stream, which are these red and blue vehicles. And the CVs, they're going to have their own sensing range to capture the information of a surrounding human-driven vehicle. And through the connectivity feature, as Dr. Labi mentioned previously, they're able to provide this information to other CVs in this traffic network. And our goal is to control this smart agent or the smart CEV together so that they can make joint driving decisions. However, achieving a decent cooperative control is not easy at all. So first, we have a problem called the highly dynamic mixed traffic environment. Basically, it means that the speed, the location, the acceleration, or driving directions of all these vehicles will keep changing over time. And also, these human-driven vehicles will introduce a lot of uncertainty to the entire system. And then we also have another challenge called the dynamic number agent problem. So at this moment, we see that there are 7 human-driven vehicles and 2 autonomous vehicles in this network. But as we go, some vehicles will join the network and some vehicle may go out. So the number of the agent is also varying over time. But for most of the machine learning and control methodologies, they typically require the input and output size to be fixed numbers instead of dynamic. And in addition, these vehicles are obviously not independent to each other. Their interactions are going to be very, very complicated, which is also quite a challenge to design a good cooperative control. So in order to address this challenge, we propose to describe the mixed traffic driving environment and the information flow topology using the graph representation. As you see here, each of the vehicle is a node in this graph. And here we have the white dot refers to the human-driven vehicles, and the blue dots are the CVs. And the CVs, as we mentioned, are able to capture the information of the surrounding human-driven vehicle within its own sensing range. So the local links in the graph here represent the information flow from the human-driven vehicle to its surrounding CV. And after getting this information, the CV are able to provide this information to other CVs in the graph through its connectivity feature. And based on that, then the graph convolutional neural network will model this communication and cooperation among the CVs. And we further introduce reinforcement learning. So in this case, deep Q learning here to train the AI to realize the end-to-end centralized multi-agent control. So we have this graph convolutional Q network that is specifically designed to take care of the dynamic number agent problem that we have just mentioned. And through this graph representation, it is also able to handle better the mixed traffic environment. Basically, it refers to traffic that will not only have the autonomous vehicle, but also the human-driven vehicle in the same time. And here we demonstrated our multi-agent control using a case study motivated by a real-world scenario when it is hard for the autonomous vehicle to do the lane changing to merge in or merge out on a highway segment. So in this case, we have two CVs. You see the red one wants to merge out at the first ramp, while the green ones have the intention to merge out on the second ramp. And we also have these human-driven vehicles to make the scenario not only more realistic, but also more complicated to see if our AI system is robust enough. And for our AI-enabled case, or this GCQ model on the top, as you see that this green vehicle will be able to understand the intention of the red CVs. So you see that it moves out from the very right lanes to create space for the red CVs so that they can merge out faster. And then there's no congestion there. Well, unlike the rule-based case, you're going to see that in a few seconds there will be some congestion start to be accumulated because of the lack of information sharing and also the lack of cooperative driving automation. You see the vehicles, they sometimes stay in the undesired lanes and kind of block the other vehicles from moving out because they only focus on what they want to do themselves instead of like caring about the other vehicles' intention. And as a result, we can see that for our AI-enabled case, as indicated by these blue bars, it has a higher overall traffic performance across different traffic density compared to the other models that we found in the literature. So here, basically, the x-axis here is the different human-driven vehicle inflow rate from the left. So basically, you can consider higher inflow rate is associated with a higher traffic density. Well, the y-axis here is accumulated model performance. It is a combination of the average speed of all the vehicle in this area and also the successful rate for the CVs to fulfill their merging intention. Right? But we can also find that this very small bar, like blue bars, indicate that the standard deviation of our AI-enabled case are very, very small, indicating that our system consistently perform well across different scenarios. The second example in today's presentation is called mitigating highway congestion in a mixed traffic stream using the connected and autonomous vehicles. I guess we all have some experience getting caught in the traffic congestion. So me and Dr. Labi are currently in West Lafayette. It's a small college town, so we're Purdue located, so maybe not here. But in general, it is quite easy for people to engage in traffic congestion because of what we saw here. You see that sometimes the people, they just all of a sudden they cut into the lane, like what these vehicles will be doing. And even if you really consider about it, those lane changing cannot really make them drive much faster, but people, they just when they have the limited information, they cannot see the downstream, so they're just going to do this. So here it shows that sometimes human drivers driving decisions are intrinsically irrational because of they have no idea about what the downstream traffic looks like besides a very short distance that they're able to see, and this could cause a lot of problems on safety, mobility, or emissions, and also potentially in shockwave propagation that can carry out these issues even away from this region of congestion, maybe even to the other places, and that could lead to even more problems. So in order to mitigate congestion, researchers and engineers in many areas have been developing many techniques in the active traffic management, including, for example, the speed harmonization, which aims to reduce the speed standard deviation of the entire traffic stream. Or they also propose method like the variable speed limit, which tries to adjust the upstream speed limit to improve the downstream condition. And we also have the ramp metering, which tries to control the inflow rate into a potential congested region. However, the traditional ATM strategies often require human drivers' compliance to be effective. But just as what we saw in the video, if sometimes the human drivers' behavior are intrinsically irrational, then this ATM strategy may not work so well in some specific cases. So in this research area, we propose to use the connected and autonomous vehicles to perform the congestion mitigation strategies that do not really rely on human drivers' compliance. The key idea here is that while the AI is learning or improving itself, it should learn to deal with how to deal with and interact with the real world data that already take into account the unexpected human driver behavior. So for the non-bottleneck related congestion, let's see a pretty famous research from about 15 years ago done by a Japanese researcher, Dr. Sugiyama. It shows the formation of what is called a phantom traffic jam, or the stop and go waves or accumulated because of human drivers' behavior. So as you saw, originally, these vehicles are pretty equally gapped between each other, and then the traffic was kind of smooth. But then some drivers, they see a gap in front of them, so they may want to accelerate to close the gap. All right, but then they may not be able to control their speed in a perfect way. So when the leading vehicle is somehow slowed down, they also need to take a sharp break, and then the vehicle follow behind them need to do the same. And the stop and go wave are starting to accumulate. And you see that sometimes this vehicle even need to take a full stop, and the traffic was not good anymore. And our idea of using the connected and autonomous vehicle to mitigate this is that when the leading vehicle is somehow need to slow down due to random behavior or whatever reason, then the CV follow behind it will get this fast enough using its own onboard sensors or through the connectivity feature, and also share this information to other CVs in the traffic stream so that they can react fast enough and control their speed in a smarter way to dampen the shock wave from accumulating. And we made a very simple video to explain this concept. And here we're going to see that the leading vehicle will need to somehow take a very sharp break. And then for these red CVs, you see that the light is already on, meaning that it will brake faster, but not as hard compared to the human-driven vehicle, the non-controlled case. And this is how it looks like when we have multiple vehicles in the stream. And as you see, by doing this, our CEV is trying to mitigate the stop and go away from accumulating and smooth the entire traffic. And that is for the non-bottleneck related congestion. Well, we have another research that is just focused on the bottleneck related congestion. So as you see in this case, we have a physical bottleneck here where we can expect a congestion. And for our AI enabled case, so here we are also applying the previous GCQ model that we talked about. You see that there are several red vehicles. So these vehicles are the connected and autonomous vehicles, and also being controlled by our own AI system. And after sensing the environment and sharing the information, talking to each other, you see that they decided to work together to form a queuing system to smooth the traffic. And from the result, we can also see that instead of having a large congested region like what does this rule-based controller does here, our AI is able to break it down into two less congested regions. So to improve the traffic throughput at this bottleneck. And also, this bar chart also shows a very similar story. For our AI enabled case as indicated by these blue bars, it has an overall higher traffic throughput compared to the other models that we find in the literature over multiple different random simulation runs. The last example in today's presentation is called collision avoidance framework for CVs under crash imminent situations. Here is an example of one of our graduate student, Mr. Trevor, driving on the road. You see that he's not only not wearing his seatbelt, but also distracted by his phone, maybe texting his friend. I think we can all agree that this is very, very dangerous, not just because he was about to hit the vehicle in front of him. If you look at the video again, right before he made that very sharp turn, there's actually another red vehicle besides him. And that could lead to a side swipe, and that may lead to a series of collisions that involve multiple vehicles into the same crash in this area. But just as a side note, that is not how Trevor drives in a normal day. The literature also talk about this, as Dr. Labi mentioned in the previous slides, the human errors. And researchers found that human errors are directly or at least indirectly related to about 95% of all the roadway crashes. This is really a huge thing. Well, there's a interesting survey show that about 88% of the drivers think that they are good or even excellent drivers. But in fact, if we think about almost all the roadway crashes are somehow due to human error, there could be some sort of overconfidence there. I'm not sure if you have heard about a term called risk compensation. So basically, in this context, it says that for people with very good driving skills, and their skill could lead to the overconfidence, right? And so the driver may feel very safe of using their own cell phones or listen to the music or even doing some other tasks. And these distractions may actually increase the crash rate for people with very good driving skills in some situations. And of course, there are several other factors like the driving fatigue or the slow reaction time. And all these will contribute to the human errors in driving. So as Dr. Labi mentioned, one of the main benefits of the future autonomous vehicle is mainly from its safety perspective, because there is really a big hope that the autonomous vehicle will significantly reduce or even completely eliminate human errors in driving. However, the deployment of the autonomous vehicle may take quite a long time. So some researchers think it may take 20, 30, or 50, or even more years before the autonomous vehicle reach a very high or even 100% market penetration. But some other researchers argue that there's no way that we can ever reach out a full market penetration, because people don't just drive their car for commuting, but some people, they really enjoy driving on their own, and there's nothing wrong about it, right? And there are also the trust issues. Some people may never use this new technology because they just don't feel comfortable of giving the control to a machine, so they just don't like or don't trust this technology. So during this very long transition period, there will be a mixed traffic. where both the autonomous vehicle and human-driven vehicles are on the road in the same time. And we believe that there will be two main perspectives of the crashes that will involve the future autonomous vehicle. The first one is when the autonomous vehicle is at fault. This is pretty self-explanatory. Reasons like system failure or mechanical issues can cause the autonomous vehicle to perform in a dangerous way. And this is also a huge concern for most of the autonomous vehicle developers and manufacturers. So naturally, it receives a lot of attention, not only just from the researchers, but also from the public or the society. Well, what we saw in Trevor's aggressive driving case is actually the perspective too. So where in this case, the autonomous vehicle may not really do something wrong or something so wrong, but there could be some human driving vehicles are at fault in the nearby area, but the autonomous vehicle may be unable to avoid those crashes. So in order to help with this perspective too, we propose the collision avoidance frameworks. So here, when a distracted driver is trying to make a very aggressive lane changing. So here, Trevor is driving these yellow vehicles and do the lane changing. And you see that these red and blue CVs are going to also talk to each other and do the cooperative driving automation and to work together to dodge the crash. And everyone receives some safety benefit in this whole area. And in this study, we consider two types of crash avoidance maneuvers, the deceleration maneuver and the lane changing maneuver. What we saw in this specific case is a lane changing maneuver. The reason that we don't want to do the deceleration for this case is that if this gray vehicle that follows the red CV is a human-driven vehicle, which is not connected, and then if the red CV tries to decelerate to avoid the yellow vehicle from hitting, then maybe due to the slow reaction time, there could be a secondary rear-end collision. So the chance for that collision could be high. So, and in that case, that is why we want these three connected ones to work together. So one blue car accelerate, one decelerate to create a gap so the red one can merge in. And from the simulation result, we can see that when the CV is very close to the following human-driven vehicles. So here, when the bumper-to-bumper distance is very small, and then if we only have this lane-changing maneuver, the deceleration maneuver as the only option, then the successful rate for these specific cases are very, very low. It's even close to 0, and also lower than 40% in most of the cases. But by enabling the lane changing maneuvers through the cooperative driving automation and also the information sharing, we are able to significantly increase the successful rate to more than 60%, even for these hard cases. And also for some other more casual cases, it's even greater than 80%. So the numbers here really depend on the real-time speed, location, and the driving directions of all the vehicle in the same area. And as you can imagine, if there's just a very aggressive human driver and really wants to hit you at a very high speed, not all the crashes can be avoided. But in that case, in the future research, we may consider to let the AI to try to find out a strategy that maybe there is so that the vehicle will be able to crash in a way, right? But will cause relatively less damage. And besides those, we have also been working on a few couple of other things. These are kind of at the early stage, but I feel some of them you might be interested in. So for example, here we have a small-scale real-world deployment to test some of our AI control framework using the Amazon debrider. As you see, this is just for like the crash avoidance maneuver that we have just mentioned. So we want to see when one vehicle is trying to do a lane changing, if the other vehicle can either decelerate or also do the lane changing to move into another lane. And also about the human factor related research, at our center, we have the EEG and eye tracker to collect data. So we can use this data to analyze the driver's brain activity or where they are paying attention to while sitting in a autonomous vehicle or just drive their own vehicle. And we're also trying to explore the options of using the virtual reality to study how human beings will be interacting with this new technology in the future. So for example, in this specific case, we're trying to see how pedestrians will interact with autonomous vehicle when they're gonna go across the street. So like normally, right, when we go across the street as human, if we see a car coming towards us, typically we are gonna look at the driver's seat. And if we know that the driver also sees us, then we'll feel more comfortable of keep going. But in the future, if it's a autonomous vehicle coming towards us, we're gonna look at the driver's seat and then we see nobody sitting there. Then what we are going to do? So using the virtual reality, it provides us the opportunity to investigate this in a safe and more realistic environment. At last, I would like to also take this opportunity to acknowledge our amazing team at Purdue Center for Connected and Automated Transportation, our center director, Dr. Labi, who has always been very, very supportive, and the student in our lab. The work you saw today is all about teamwork. We have many talented and hardworking students, and without their dedication, there's no way that we can come to this far. Here are the references, basically about all the work that we did in this presentation. And thank you very much for your attention. We would like to take any questions or comments that you may have. Thank you.
Thank you so much. Thank you for giving us almost the same exact 15 minutes that I requested at the beginning. So I think now we should have time for questions. Any question?
Okay, good afternoon. I really enjoy both talk. Can we go to slide number 26?
Okay, one moment.
So
It's
you're
26.
making an assumption.
Right.
A, we have vehicle-to-vehicle communication, and B, you're making an assumption that surrounding vehicles are going to be collaborating with one each other. But and then you mentioned you improve the performance by over 60%. But can you really trust the drivers that are in the mode of collaborating with one each other?
Yeah.
The crash.
Yeah. Yeah, so thank you for bringing that out. That is actually a very, very important point. So in this specific study, we are trying to make the case simple, as you said, right? Since at this stage, we are trying to see if there's a potential to use this AI to learn how to respond well. But you mentioned a very, very important point. Since, so for example, in the future, right? Maybe let's assume we have a very high market penetration. Everybody uses the autonomous vehicle. However, maybe I'm sitting in the Lyft vehicle and you are sitting in a Waymo vehicle. So we are using the autonomous vehicle from different companies, and maybe they don't like to share information to the vehicle to other companies, right? So because these tech companies are competing with each other, and also they are due to other privacy issues, and maybe like people don't feel comfortable about sharing their like driving direction or data or intention even to the other vehicle, even for their own benefit. So I think this will be a very large and interdisciplinary future research area. And my current opinion is that maybe we as a researcher should study this AI and technology and then try to provide some suggestions to maybe to the government or to the public agencies. Because to me, I feel it's pretty impossible for different tech companies to just have the agreement and then they just start to work together. Right? Yeah. Yeah, so thank you very much to bring that out. I think it's a very interesting point.
Okay, thank you.
So while we are here, I have also one question. This case study and use case is very interesting, but it's really sort of limited sort of scenarios that you can think of. I'm not saying that I mean is sort of, I would call it, might be it may not be I mean it may not be sufficient enough to conclude that, hey, connectivity may reduce or how much is going to be effective as far as reducing the crashes. So
Right.
maybe how about thinking, I mean, with this similar approach, but in a congested road, that you can all of a sudden create a sort of stop or whatever sort of inject a sort of accidents or stops or whatever, and see under different penetration rates of AVs and connectivity that you do have, then how much we can expect the improvement and reduction of the accidents. And of course, in that situation, everything has to be random, right? You randomly, and you have to go through different cycles of creating events, crashes, and see how that happens. Do you think that have you been doing that kind of a study, or do you have it in your plan to do that?
Yeah, I think all those are fantastic ideas. So actually, we are trying to do a small part of what you just described, but then you mentioned many new ideas. So just in the last week's group meeting, so Dr. Labi and the students, so we are trying to design some scenarios. Maybe in the mixed traffic, some vehicle will like take a stop or whatever, right? And then we are trying to see if we can collect some data about the lane changing trajectory or how people react, like how much time they need to react. And then we are trying to combine this with our autonomous driving framework. So we are still trying to explore different ways of putting all this information together. Yeah, thank you for the comments. Those are very interesting ideas. Yeah.
Yes. So that's right. So what we show here is a very simplified scenario for the audience to understand. As he is describing, is a wider set of scenarios with different traffic conditions. Absolutely, that's something that we shall be looking at, and like Sikai said, we are, as of now, we are creating different environments, different scenarios to capture some more complexity in the traffic stream. But this presentation here was a very basic one, just to illustrate the concepts of what we later. Yeah.
Exactly. That's a great proof of concept, but then later to the concept, and then for the proof, and then seeing that, I'm sure that in that sort of scenarios we can see statistically how that can result in improvement.
Oh yeah.
Yeah.
And the benefits for a more complex traffic stream in a dense urban area will be much more than what we showed. What we showed is that even for this simple scenario, the difference in benefit is so obvious, right? Then for a complex network, I mean, the benefits from that are going to be much more, because you are getting more interactions, and there are more. There's more traffic volume, and more potential accidents, and more opportunities for inefficient way of movement. So at this point going forward, we can expect much more benefits, if you apply this method,
Of course,
but not less, no way less, but much more.
Right. And one other point in the same experiment that I just mentioned, one of the claims when people are trying to use CAVs and so on, the claim is that with the CAVs there is a possibility to increase the capacity of the roads, and the cars can drive closer or whatever. But when it comes to the accidents and those sort of situation, that hypothetically may increase the sort of chances of crashes. So then, while reducing the distance and then applying this sort of risk mitigation that we do have here, what is the limits? How much we can get close, and then how much we can still improve, take advantage of safety, additional safety that CAVs are bringing.
Right. Yeah, I just want to add a little bit more. I think all those are very good thoughts, and I think the reason that this new technology creates a lot of new opportunities is because, for example, we can also maybe consider from the cybersecurity perspective, right? Since in order to let this sort of system to work well, these vehicles needs to constantly sharing information along the way that they're driving. So if we cannot protect this information like security, then it will be easy for people to send out fake information and cause some big problems, right? So I think this is just one example that like there are many factors need to be put together so we can have a better understanding about what the future really looks like.
And you know, in the long term, prospectively, maybe 50 years from now, let's assume extreme case where every vehicle is a CAV, right? Then in that case, there'll be definitely higher safety, higher mobility, right? Efficiency, definitely. And there'll be that gap. There'll be a small gap, right? Because it's like a train that's moving, right? So definitely. However, before we get to that stage, where it's a transition period where the traffic is mixed, human vehicle and CAVs, it's not going to be so easy to achieve those efficiencies and those safety benefits. You know, as a matter of fact, in the short term, after CAVs are allowed to use the roads, maybe the first 2 to 5 years, we expect an increase in crashes because people will now start getting used to CAVs. But thereafter, then we believe that the benefits of in crash reduction will kick in. So the crashes will go up initially, and then it will come much lower than what we have now. You know, so we don't expect a decrease in crashes as soon as the CAVs are deployed. No, we think that there'll be some learning pains. There'll be some pains in learning and in getting adjusted to this new technology, and that may cause an increase in crashes. But we don't expect that to last long. It will be for a few years. Then after that, we shall start seeing the safety benefits of CAVs. And at some point, yes, Ali, you are right. There might be some trade-offs between safety and mobility at some point, you know. But beyond a certain market penetration, we expect that both will be increased. Both efficiency and safety will go up.
Right. Okay. Great. Thank you. So, any other questions?
I have a quick question. First of all, it's a very nice work and very nice presentation. So, as the statistical data showing for collision evidence framework utilizing the AI, these are simulated data, right? And
Yeah.
if
I'm sorry. So could you maybe speak louder?
Okay.
I'm sorry.
I mean, just sorry for that. Can you hear me good now?
Yes.
Yes, much louder now. Yes.
All right. The collision evidence framework utilizing the AI, the improvement of performance showing based on the simulated data, right?
Yes, simulated. The driving simulation environment.
Okay. So as it is a simulated data, but when it will be implemented in the real world scenario, how confident you are that your model will perform as the simulated data and it will work properly? I don't know. This is the
right. Why don't you pull up the place where you have the hallway? Actually, we actually did this in the real world, but not on the roads. This is a hallway of our offices where we put some tape on the ground to show for pavement markings or some tape, white tape, and we have 2 small vehicles that had the algorithm, and we tested it. You know, so there was a kind of small scale but real life demonstration. You know, so we moved from the driving simulator to this. From this, we are going to move to a go-kart, which is like a small vehicle with its own track. You know, and from that, the intention is to go to a real vehicle on a real road. So we are in stages. We have shown this on the we have shown this using these small vehicles in a hallway of our office. We're going to show this on a test on a go-kart and then an actual real life real vehicle. So the stage of deployment in codes that we are using, you know, and we expect that there'll be no loss of scalability, you know, as we go up from simulation to real life deployment. We are to see, but we are very confident in our AI. But it's a good question. Great question.
Yeah, because I believe it will work, but there are a lot of additional challenges that will come when we
absolutely as everything else. Yes,
real world application. And also,
so you're perfectly correct. I just want to add one point. Like related to what you said. So basically here, one very strong assumption I have to admit that we made is that we are assuming this vehicle can receive the other vehicle's information instantly, but this is definitely cannot be true in the real world, since during the real world scenario, there will be information transmission delay, right? So that's why like 5G is very important in this context. Like now people are trying to say like we have to have 5G to let this sort of a framework to work well, right? So we need to reduce the chance for the packet loss and also for the information delay. So one potential small marginal improvement of this research in the future area is to consider like we can also simulate some sort of information loss and information delay and see how that will change this simulation result. Yeah, but as you said, there are also other issues like from the mechanical side, from the electrical engineering side, and so on. So, so that's why like we want to have this more realistic real-world deployment related research to try to have all those data.
Yes, perfectly so. Because even in our real life hallway experiment, as you can see here, you know, it was in a corridor with carpet. Everything was so good. No rain, no snow, you know, none of those things. So it was a perfect environment to work with. But Mohammed, in the real life, just like you said, there might be some conditions that will prevent the algorithm from performing very well. Even though we are confident in the algorithm, there are some things that you just can't control, you know, and these are going to impair the performance. Like Sikai said, sometimes it's loss of information because an AV, what does an AV do? An AV senses, right? It senses the environment, collects the data on the environment, then through connectivity, it also gets data. It fuses these two together and makes a decision based on the two. There's temporal time delay in the information transfer to the AV. There's time delay in the processing of the information, the fusion of the information. There's time delay in the deciding, making the decisions. You know, it's a few seconds, yes, but it's still a delay, right? Even if it's 0.05 seconds, it's still a delay. So all those things in practical reality could, you know, make the algorithm, you know, less efficient than the driving simulation environment, you know, and that's a great point, Mohammed. That's a great point.
Thank you. Thank you so much for clarifying all of this thing.
Welcome.
And again, thank you so much for this nice presentation.
Yeah, thank you.
Thank you.
Any other question?
I have a question. Thank you, Dr. Samuel and Dr. Sikai for your presentation.